Hey everyone, welcome back. And today we're going to look at another common application of the gambler's room problem, which is calculating the expected stopping time. So if you remember in the last video, a gambler's room problem is when we have a person and they have I dollars at the beginning. So they will gamble $1 at a time with a certain win rate. In this case, we're going to say P is 50%. So every time we have a 50% chance of gaining $1 or losing $1. So we're going to continue playing this game until we either have $N or $0. So we either gained money until we have N dollars or we lost money until we have $0. So in either of these two cases, we want to find out how long this process took, and we want to find the expected value of the time it took. So let's introduce a new notation here. Let's say that E of ti, this is the expected time for us to finish at I dollars. So suppose we have I dollars and we want to know how long it takes to finish starting from I dollars. So when we have ETI, there's two different states we can go to. So at I, we can either gain $1 or lose $1. Since this question said we have a 50-50 chance of winning or losing, we can say there's a 1/2 chance. We go to the next state, which is going to be Ti minus 1. Say we lost $1, or we could have gained $1. So 1/2 chance of E at Ti plus 1. So these are all equally possible. We can either lose or we can win. But either of these takes one timestamp. So it takes the single bet here to reach one of these two states. So the expected time at T of I is a recursive relation depending on T of I minus 1, T of I plus 1, and also adding 1 to that because it took this one gamble to reach that new state. And each of these two states have a 50-50 chance of appearing. So in this case, we can do a recursive solving just like before. First of all, by doing 1/2 plus 1/2 in brackets here to E of T of I. So this doesn't change the equation at all, but instead we can split this and split E of Ti into two different equations. So now we have 1/2 in brackets expected time at Ti minus the expected time Ti minus 1. So this is going to equal to it should be just 1 here, plus 1/2 E expected value of Ti plus 1 minus the expected time at Ti. So here we're just shifting the variables in the equation around, and then we notice we can get rid of these 1/2s and just change this 1 into a 2, which is what I wanted to do earlier. So let's get rid of all these brackets, parentheses here, and we have a brand new equation. So again, this is the difference of a bunch of differences of consecutive terms. So when we have a difference of consecutive terms, then we're able to apply the formula we did in the last video by adding these consecutive terms up. But before we do that, we should take a look at the extreme cases. For example, when I equals to 1. So let's look at this case first. Here, I equals to 1. If I equals to 1, then we get the expected time at T1. This minus the expected time at T0, which is 1 minus 1. This is going to equal to 2 plus the expected time at T2 minus expected time at T1. So we know that once we reached 0, then we don't have to play the game anymore. So the expected time at T0 is going to be 0. We already reached the final state. So we can do this again. For example, we have the expected time of T2. So E of T2, this is going minus expected time of T1. This is going to be equal to 2 plus the expected time at T3 minus the expected time T2. And we can do this so on and so forth. But before we do that, we should notice that this term right here, so E of T2 minus T1, is identical to this term right here. So we can use substitution and we can get that E of T1, let's actually just write on blue here, E T1 this is going to equal to 2 plus ET3 minus ET2. So because we moved this term down here to be here, since all of these two are equal. So let's do one more case. So let's say E of t3 minus E of t2. So we know that this is going to be equal to 2 plus E of t4 minus E t3. So then we can take this term here and move it down here, because this is equal to this. Sorry, 1 second. So this is equal to this, so we can replace it with the right-hand side. So we can expand our equation here, which is equal to 2 plus 2 plus 2 plus E of t4 minus E of t3. So we can keep expanding this, and we're going to get a bunch of 2's all the way until we reach t of n. So we can keep doing this same process over and over again until we get 2 plus 2 plus 2 plus a bunch of 2's plus 2 plus until we reach the final condition, which is E of tn. This is our final state, minus E tn minus 1. So we know that at tn, we don't have to play this game anymore, so this term goes to 0. And now we want to find out how many 2's there are in this bunch of 2's here. So notice that when we have t3, there's 2 2's, t4, there's 3 2's. So when we reach tn, there's going to be n minus 1 2's. So it's going to be 2 times n minus 1. E of tn is going to be 0. This is 0. So all we have to subtract is E tn minus 1. So we got that E t1 is equal to 2 times, in brackets, n minus 1 minus E of tn minus 1. So something that we have to notice here is that E of t1 is symmetrical to E of tn minus 1. So in Gambler's Ruin, we can visualize our wealth on a line here. So this is $0, this is $n, and E of t1 is going to be when we have $1 right here. Whereas E of tn minus 1 is when we have n minus $1 right here. So either of these two conditions are going to have the same expected time, because we have a 50-50 chance of going left or going right. So we can also imagine this as, for example, walking on a road, and then how long it takes to reach either side of the road. So at 1 here, it takes 1 step to go to the left, or it takes n minus 1 steps to go to the right. So notice how this is identical to being at n minus 1. We can take 1 step to the right, or we can take n minus 1 steps to the left. So these should have the same expected time, because going left and going right is the same. They have the same probability. So hopefully that makes sense, and we can justify that E of tn minus 1 is going to be equal to E of t1. So this term here, let's write it in a different color. This term is going to be equal to E t1. That means we can bring this onto the left-hand side, so we get 2E t1 is going to equal to 2n minus 1. So we can cancel out these 2 here. So now we got that E of t1 is going to equal to n minus 1. This is a really nice result, because this no longer depends on E of t1 minus 1 minus 1 or 1 plus 1. This is no longer recursive, and it's just dependent on n and 1. So n minus 1. So now we want to find a generalized formula. We don't just care about t1, we also care about a bunch of different ones. For example, what is expected time of t2, t3, and so on. So now we can bring this equation from before all the way down. Let's make a duplicate of this. So let's get rid of this term here, since that's 0. And we can move the other t1 onto the left-hand side. So 2E of t1, getting rid of this E of t1 here. And this is going to equal to 2 plus E of t2. We know that E of t1 is going to equal to n minus 1. So expected time of t2, this is going to be equal to n minus 3. Whoops, I forgot the 2 here. So this should be 2e of t1. Let's go back one step. So this is going to equal to 2 times n minus 1. So moving everything to the right, we get e of t2. The expected time at t2 is going to equal to 2n minus 2. So we can do the same process for the next one, which is going to be t3. Let's just do that so we're confident in our answer here. So let's duplicate this over. So we know that e of t2, let's move everything here, 2e of t2 is going to equal to 2 plus e of t3, subtracted by e of t1. So changing everything in forms of n, so it's going to be 4n minus 2 minus n plus 1 equals to 2 plus e of t3. So this is going to be 4n minus 8 minus n plus 1 minus 2 equals to e of t3. So this is going to be equal to 3n minus 9, or if we factor out the 3, it's going to be 3n minus 3 equals to e of t3. So hopefully we see the pattern here. So e of t1 is n minus 1, or 1 times n minus 1. E of t2 is 2 times n minus 2. And e of t3 is going to be 3 times n minus 3. So the pattern that we can notice here is e of ti is equal to I times n minus I. Finally, we have an equation that is not recursive, and we're actually able to express the expected time based on just n and I. So this isn't a formal proof for this. This is just a general way for us to notice a pattern here, and we're able to apply this pattern to get an answer for our question. So the expected time at t of I is just going to be I times n minus I. And conceptually, we can try plugging in some i's to see if it makes sense or not. So for example, we have the extreme cases where I equals to 0 or n, and both of these cases are going to yield an expected time of 0, and that makes sense because we're already at the destination. We don't have to move anymore. So for example, if I is going to be 1, that's still pretty close to 0 since it's 1 times n minus 1, and that's going to be the exact same as I equals to n minus 1. Since it's going to be n minus 1 times 1, which is the same. So as as I gets closer and closer to half of n, we're going to get the largest expected time because, for example, our money is in the middle. It's in the middle between $0 and $n. So it's going to take the longest time for us to reach either of the two sides. So this answer makes sense to us intuitively as well. So finally, with this expected time out of the way, we can move on to a very difficult problem, but this, using the gambler's rune strategy, is actually very solvable. So the problem goes like this. There's 12 people. Let's actually draw a diagram here. There's 12 people seated in a circle, just like a clock. So 12 is at the top. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And the person at the 12th spot, this person right here, this is the host of the game, and the host is going to give a present. So let's draw a present. Let's just say this present is a blue dot, and this host has a 50-50 chance of passing it to the left or the right person. So the host could either pass it to 1 or pass it to 11. So suppose the host passed it to 1 without loss of generality, then 1 could either pass it to 2 or pass it back to the host at 12 with 50-50 chance. So either of these outcomes are exactly the same chance. And the game goes like this. The last person to touch this gift is going to be the winner of the game. So for example, if everyone touched this gift, everyone here except 6, and then for example, 6 got the gift afterwards, then 6 is going to be the winner of the game. So, or if the gift goes like this, it goes all the way to 3, then it goes all the way back, and it comes to 3. 3 is going to be the last, 4 is going to be the last person to touch the gift. So 4 is going to be the winner of this game. So suppose you can choose where you sit, and you cannot be the host, because the host is guaranteed to lose the game. Out of these 11 spots, which spot would you choose? So immediately looking at this question, this doesn't look like anything close to Gambler's Ruin, since we don't actually know with the starting amount of money. We don't know $I, we also don't know $N, so it looks like we can't apply any of the formulas we derived earlier. However, looking at this question in a different way, it actually is exactly a Gambler's Ruin problem. Because suppose, with a loss of generality, let's take a look at 3 here. So for 3 to win, what has to happen? 2 has to touch the gift first, and then 4 has to touch the gift afterward. So both 2 and 4 must have touched the gift. If 2 and 4 both touch the gift, that means everyone in this arc between 2 and 4 has already touched the gift. And at the same time, 3 has to have not touched the gift. So essentially, we need the gift to either go to 2 or the gift to go to all the way to 4. And once the gift is at 2, for example, we need a Gambler's Ruin run of all of this all the way back to 4. So once the gift is at 4, then we have a guaranteed chance of winning since everyone touched the gift except 3. That means 3 is guaranteed to lose the game. To win the game eventually. So what is the chance that the gift is going to eventually go to 2 or eventually go to 4 without 3 touching it? It is actually 100%. Because the gift, to be able to touch 3, has to either go down here through 2, or it has to loop all the way around through 4. So for person 3, we know that before we receive the gift, either 2 or 4 must have touched the gift. So we can start a Gambler's Ruin sequence, starting at either 2 or 4 when they touch the gift. So suppose, just without loss of generality, let's say 2 touch the gift is at 2. Then we have, let's say this is going to be $1. At 3, we don't want to come back to 3 before 4. That means we must have lost the game. So let's say 3 here is going to be $0. So we can label all these people as currency amounts: $3, $4, $5, $6, $7, $8, $9, $10, and $11. So we need a Gambler's Ruin run of all the way to 11 without losing this 1. So instead of this difficult problem right here, we converted it to a Gambler's Ruin problem where n equals to $11, I, the starting amount, equals to $1. And we're ruined the moment we go back to 3 because we don't want 3 to be touched before 4. So knowing that we have a formula for this, what is the chance of us winning given both and r is equal to 1 over 2, since each person has a 50-50 chance of passing it to the left or passing it to the right. So from the equations we derived in the last video, we know that p of j, this is going to equal to 1 over n times j if r equals to 1 over 2. R equals to 1, not 1 over 2. R is the common factor and p equals 1 over 2. So the probability of going either way is 1 over 2. So if p equals to 1 over 2. So we know that p of 1 is going to equal to 1 over n times 1. N is going to be 11 in this case. So the chance of us winning seated at 3 is going to be 1 in 11. And this actually makes sense because there's going to be 11 different people. There's 11 different players excluding the host, and they all have a 1 in 11 chance of winning. So if that doesn't make sense to you, for example, if you think 6 has a higher chance of winning, let's actually clear everything right here. We can do the same problem from the perspective of number 6. So at 6, we either have 5 have the gift or 7 have the gift before 6 does. So suppose 7 does, that means we can either go back. So 6 is going to be $0, 7 is going to be $1, or we can make a Gambler's Ruin run all the way to 5, which is going to be $11. Drew this arrow too long, so it's going to be here. So again, it's going to be a case where n equals to $11, I equals to $1, and p equals to 1 over 2. So plugging into the formula, again, we're going to get p of 1 is going to equal to 1 over 11. So doing this for every single person in the circle except the host, we're all going to get 1 over 11. So no matter where we sit, we're all going to have an equal chance of winning this game. So this question is one of my favorite applications of Gambler's Ruin in a difficult probability question. And this question very well disguises Gambler's Ruin, so it doesn't seem like we can apply the formula. But once we notice that it's essentially we have to have a Gambler's Ruin run of 11 to 1 for us to win the game, then we can apply the formula and just solve the question. So that's it for this question, and that's it for the series on Gambler's Ruin. Hopefully you guys were able to learn something, and I'll see you in the next video.